this problem, we will utilize the Nernst equation, which is calculating the deltaG of a reaction, but the only difference is we're not at standard state conditions. So two things. Number one is deltaG by itself, no superscript or anything, it's just deltaG, non-standard state conditions. And then our pressures, these are gases, our pressures are not at 1 atmosphere, so we're at non-standard state. This is the perfect opportunity to use the Nernst equation. So the Nernst equation is shown here. Is for non-standard state conditions. We're going to use Q here. Now if Q is equal to K, then we are at equilibrium, so we can assume that we are at standard state. But if Q is not equal to K, the reaction will adjust itself accordingly so that the equilibrium is maintained. If Q is equal to K, then you're okay, simply because your deltaG at non-standard state is equal to the deltaG at standard state. But if your Q reaction quotient does not equal to K, then your reaction is going to move to compensate. It will either shift to the product side, it will either shift to the reactant side. This is accordingly based on Le Chatelier's principle. The reaction will move to establish that equilibrium based on whether K is greater than, whether Q is greater than K or whether Q is less than K. So the reaction quotient here is the same equation as K, but remember we use Q to compare to K. So products over reactants, and this is balanced. So it's going to be the pressure of H2O. I'm using pressure instead of concentrations because if you look closely at the problem, they give atmospheres, so it's pressure. So here it's going to be pressure of H2O times the pressure of CO, products over reactants, divided by the pressure of H2 gas times the pressure of CO2 gas. In order to calculate at non-standard state, you need the standard state values. So we'll do that for this equation here. Sum of the products minus sum of the reactants. So for CO gas, carbon monoxide gas, I looked it up and got a value of minus 137.17 kilojoules per mole. Plus H2O gas, make sure you choose it for gas, not liquid or solid, and that's going to be a minus 228.57 kilojoules per mole. Okay, this is stuff that you just look up in the back of our book. Minus, okay, you're going to put a big parentheses here, H2 gas is 0, that's a natural abundance, plus CO2 gas, which is plus a minus 394.36 kilojoules per mole. Doing this on my calculator, getting a deltaG at standard state, because using the values from the back of the book, of 28.62 kilojoules per mole. Right, so we can plug that in here and go ahead and move on to part B. In part B, they actually give us the pressures that we can use to solve for Q, okay, to get Q and see where the reaction will shift. All right, comparing Q to K. All right, so calculating our reaction quotient here, let's look at our values of our pressure here. We got H2 at 0.25 atmospheres, CO2 at 0.78 atmospheres. So 0.25 Q does not have units, just like K. It's used in comparison to K. H2O given to us in this problem is 0.66 atmospheres. Again, I'm not putting units here because Q, just like K, has no units. And carbon monoxide, CO, is 1.20 atmospheres. So I'm getting 4.06 when I calculate reaction quotient Q. The actual equilibrium constant, that's pretty close here, the actual equilibrium constant is 4.40. So remember we put Q first, comparing it to K. We got 4.06 given to us at this specific temperature, 4.40. We use the Gator rule, and we find out that alligator jaws are pointing to the right-hand side. So we're not at equilibrium, but to achieve equilibrium, this specific reaction is going to go to the right. So let's calculate our deltaG under these non-standard state conditions. We already got deltaG naught from utilizing products minus reactants. Let's go ahead and get that to joules per mole. So that's going to be 28,620 joules per mole. Plus R is 8.314 joules over mole Kelvin times T. T here is 22,000 Kelvin. T is 2,000 Kelvin. And all of that times natural log of Q. We already solved for Q here, putting in the pressures they gave us in the problem, and that was 4.06. So this will be our answer to this problem. This is our Nernst equation application, calculating free energy changes under non-standard state conditions. So natural log of 4.06 times 2,000 K times 8.314 gives us about 23,299. We want to put units to Kelvin. Kelvin cancel. 23,299 joules over mole plus the 28,620 joules over mole here. That's going to equal to our delta G, and I'm getting a delta G value, adding those together, of about 51,000. Well, let's go ahead and do that here. Plus our 28,620, 51,919 joules per mole. So under non-standard state conditions, this is endergonic, okay, under these pressures, and at 2,000 Kelvin, it's endergonic. We can go ahead and change that to kilojoules per mole, dividing it by 1,000. It's about 51.9 kilojoules per mole. You can even say 52 kilojoules per mole, and that is the answer. So notice at standard state conditions, it's one value. When we change the pressures and change the temperatures, we get a whole different value. That is utilizing the Nernst equation. When Q is utilized, and Q is, again, compared to K, tells us which way the reaction will shift to get to equilibrium.